Hello, and welcome to G Fun Facts Online, the show where we dive deep into the science and stories behind our world. Today, we're venturing out onto the high seas. The ocean has always been a place of immense power, a testament to human ingenuity, but also a stark reminder of our limitations. We look at modern ships, these colossal floating cities and warehouses, and we feel safe. We think we've conquered the waves. But the 21st century has proven that the sea is never truly tamed. Today, we're exploring the stories of modern maritime disasters. These aren't tales from the age of sail. These are tragedies from our lifetime, born from catastrophic engineering failures. Each wreck, each loss, is a grim but vital lesson that has fundamentally reshaped how we build ships and navigate the world's oceans. So grab your life vest as we explore the engineering breakdowns that led to disaster at sea. First up, we need to talk about a type of ship that completely changed travel, the roll-on/roll-off ferry, or RORO ferry. Think of it as a giant floating parking garage. You drive your car or truck straight onto a massive open deck, and then you head upstairs to the passenger areas. It's incredibly convenient. But this convenience came with a hidden and deadly design flaw. That cavernous vehicle deck was completely open, with no internal walls or bulkheads to stop water from moving around. If water gets onto that deck, it can slosh from one side to the other, unimpeded. This is called the free surface effect, and it can cause a ship to lose stability and capsize with terrifying speed. Two tragedies brutally exposed this vulnerability. Our first story takes place on the evening of March 6, 1987. The RORO ferry Herald of Free Enterprise had just left the Belgian port of Zeebrugge. Just minutes into its journey, it began to list heavily. Within 90 seconds, it had completely capsized in the shallow water. 193 people lost their lives. The immediate cause was almost unbelievably simple. The bow doors, the giant doors at the front of the ship that vehicles drive through, had been left wide open. As the ferry gained speed, water poured onto the open vehicle deck. The free surface effect took over instantly, and the ship was doomed. A lucky turn grounded it on a sandbar, which prevented it from sinking completely and saved hundreds more lives. The official inquiry uncovered a shocking culture of negligence. The crew member responsible for closing the doors was asleep in his cabin. His supervisor had already left his post. And critically, there was no indicator light on the bridge to tell the captain whether the doors were actually closed. He simply assumed they were. But beyond the human error, the investigation pointed squarely at the ship's design. The open vehicle deck meant that once the water was in, a capsize was almost inevitable. The disaster of the Herald of Free Enterprise was a direct catalyst for creating the International Safety Management Code, or ISM code. This made it mandatory for all shipping companies to have a documented safety system, with checklists and procedures to ensure an accident like this could never happen again. Just 7 years later, on a stormy night in the Baltic Sea, the same design flaw would lead to an even greater tragedy. On September 28, 1994, the MS Estonia was sailing from Tallinn to Stockholm. The weather was rough, with waves slamming against the ship's bow. Suddenly, passengers heard a loud metallic bang. The ship quickly developed a severe list. Within an hour, the Estonia sank, taking 852 lives with her in one of the worst peacetime maritime disasters of the 20th century. The investigation found that the locks on the bow visor had failed under the relentless pounding of the waves. The visor is the outermost part of the bow door that lifts up like a garage door. When its locks failed, the 50-ton steel visor was torn off the ship. This, in turn, pulled the inner ramp open, allowing thousands of tons of water to flood the car deck. Just like with the Herald, the free surface effect took hold, and the Estonia capsized and sank. Investigators discovered that the design of the bow visor was critically flawed. It was built to standards for a fixed, non-opening bow, not one that had to withstand the dynamic forces of the sea. The tragedy led to sweeping changes. The International Maritime Organization mandated stronger bow visors, better watertight designs, and required the installation of voyage data recorders, the maritime equivalent of an airplane's black box, to help investigators understand future accidents. From ferries, we now move to the true giants of the sea, bulk carriers and container ships. These vessels are so immense that their very size creates unique engineering challenges. The sheer weight of their cargo and the constant flexing from ocean waves puts unimaginable stress on their hulls. One of the most haunting maritime mysteries involves one of these giants. In September 1980, the MV Derbyshire, the largest British ship ever lost at sea, was carrying 150,000 tons of iron ore when it sailed into the path of Typhoon Orchid off the coast of Japan. And then it vanished. No distress call, no wreckage, no survivors. All 44 people on board were gone. For 14 years, its fate was a complete mystery. Finally, in 1994, the wreck was found at a depth of 4 kilometers, and a deep-sea forensic investigation could begin. What they found was a slow, creeping structural failure. The investigation concluded that massive waves from the typhoon were crashing over the bow. This damaged the covers of small ventilator pipes on the deck. It seems minor, but this allowed seawater to slowly flood the forward compartments of the ship. As these compartments filled, the bow sank lower and lower into the water. This put immense pressure on the massive forward hatch covers. Eventually, the number 1 hatch cover failed and collapsed, and the ocean rushed into the cargo hold. The ship would have gone down in minutes. The crew were cleared of any wrongdoing. The disaster revealed a critical vulnerability in the design of these ships, leading to new international standards for the strength of hatch covers and the protection of deck fittings. But what happens when the ship itself fails? On June 17, 2013, the container ship MOL Comfort, only 5 years old, was sailing in the Indian Ocean when it encountered heavy weather. And then it did the unthinkable. It broke in two. The hull girder, the main structure that gives a ship its longitudinal strength, failed completely. The entire crew of 26 was thankfully rescued, but both halves of the massive ship, along with over 4,000 containers, eventually sank. The incident sent a shockwave through the shipping world. How could a nearly new ship, built by a top shipyard, suffer such a catastrophic failure? Investigations pointed to a phenomenon called longitudinal bending stress. Imagine a ship riding a massive wave. The bow and stern are supported by water, but the middle of the ship, full of heavy cargo, is sagging in the trough. Then, moments later, the middle of the ship is on the crest of a wave, and the bow and stern are sagging. This constant hogging and sagging motion puts incredible stress on the hull. The investigation suggested that a structural flaw, combined with the way the cargo was loaded, created stresses that exceeded the hull's strength, causing the bottom plates to buckle and the ship to fracture. As a result, all of the MOL Comfort's sister ships were immediately pulled from service and reinforced to prevent another ship from simply snapping in half. But it's not always the hull that fails. Sometimes, it's the systems inside. On October 1, 2015, the U.S. cargo ship Faro sailed directly into the path of Hurricane Joaquin. It sank, with the loss of all 33 crew members. A key engineering failure here was the loss of propulsion. The ship was listing, or tilting, so severely in the storm that the main engine's lubricating oil pump lost suction, meaning it started sucking air instead of oil. This caused the engine to shut down automatically. Without its engine, the Faro was dead in the water, completely at the mercy of the hurricane's 150-mile-per-hour winds and 40-foot seas. The investigation also revealed outdated weather information and a breakdown in communication on the bridge. The lesson from Faro was clear. Critical engineering systems, like propulsion, must be designed to function even when a ship is in extreme conditions. And this brings us to a very recent event that many of you will remember. On March 26, 2024, the container ship Dali lost power as it was navigating out of Baltimore Harbor. It drifted, uncontrollable, into a support pier of the Francis Scott Key Bridge, causing a catastrophic collapse that killed 6 construction workers on the bridge. This disaster wasn't about a storm or a structural failure of the hull, but a failure of the ship's complex power systems. A modern vessel like the Dali is a floating power plant, completely reliant on electricity for steering, navigation, and propulsion. A total blackout leaves a 100,000-ton vessel drifting like a ghost ship. The Dali incident is a wake-up call, highlighting just how vulnerable our critical infrastructure is to a single point of failure on one of these maritime giants. So who oversees all of this? Behind the scenes are organizations called classification societies. They are the unseen guardians, setting the technical standards for how ships are designed, built, and maintained. Along with the UN's International Maritime Organization, they are responsible for turning the painful lessons from these disasters into new, stronger regulations. The history of maritime safety is, in a way, a history written in tragedy. Disasters like the Titanic, the Herald of Free Enterprise, the MS Estonia, the Derbyshire, and the Faro were the terrible catalysts for the most important safety improvements we have today. Each investigation, each report, and tragically, each life lost, contributes to a global knowledge base that aims to prevent the next catastrophe. Modern maritime disasters are a stark reminder that our mastery over the ocean is an illusion. They drive the evolution of engineering, force us to create more robust procedures, and strengthen our resolve to enforce safety. The journey is ongoing because the unforgiving nature of the sea demands nothing less than our constant vigilance and a relentless pursuit of improvement. Thanks for listening to G Fun Facts Online. Join us next time as we uncover more fascinating stories from the world of science and engineering.